Good afternoon, everybody. My name is Carl Mitroff. I am the AeroDef Conference Manager. Thank you for joining us today for SME's Technical Community and AeroDef Manufacturing Satellite Session. We appreciate you taking time out of your day to join us. Before we get going, I have a few housekeeping items I'd like to cover. You'll recognize right away that your microphones have been automatically muted. If you do have questions regarding the webinar functionality, please use the chat feature in the web page. If you have technical questions and would like to ask our speakers, you can submit them using the Q&A function. We'll be monitoring both. In the event of any technical glitches, we will be recording this presentation and it will be made available on our AeroDef website after this meeting. Today's webinar, New and Emerging High-Performance Polymer Additive Manufacturing Materials and Processes, will look at new, emerging and established additive manufacturing methods of polymers for aerospace applications and dive into the benefits and challenges as well as history and application. Hosting today's webinar is Eric Barnes. Eric Barnes is an additive manufacturing senior fellow at Northrop Grumman Corporation with over 30 years of experience. He is responsible for the aerospace systems sector additive manufacturing technology portfolio and integration of additive manufacturing across all of Northrop Grumman. He has led the development, implementation, and strategy for polymer and metallic additive manufacturing on multiple air and space programs. Eric has 3 additive manufacturing patents and 8 patents pending. On top of that, he is a valuable contributor and AeroDef conference advisor on our conference committee. Thank you very much, Eric, for your time. I really appreciate it and for hosting today's webinar. I'll kick it off to you.
All right, great. Thank you, everyone. I'm glad you could all make it. I'm glad all the attendees could make it to participate in the webinar. First, I'm going to kick this off by presenting our other speakers. First is Regina Penn. She has over 10 years experience in aerospace, owning engineering, fabrication, testing, and qualification of complex engineered systems on hydromechanical, electromechanical control systems on commercial and defense platforms. In 2017, she joined OPM, which was eventually bought by Hexcel and became the Hexcel additive manufacturing today. She leads the materials and process engineering and the program management teams at Hexcel Additive Manufacturing in Hartford, Connecticut. She has a bachelor's in mechanical engineering and a master's in systems engineering from Stevens Institute of Technology. Our other speaker, our other panelist today, is Joshua Martin from Fortify, PhD and CEO of the corporation. He is a mechanical engineer and a material scientist by training, has a BS mechanical engineering from the University of Delaware, where he was first exposed to composite materials. He was a material scientist at the Army Research Lab before moving to Boston to pursue his PhD at Northeastern University under an NSF fellowship. His research spun into Fortify, where he operates as CEO. Okay, with that, I'm going to dive into my presentation. You can go to the next chart, please. I'm going to give an aerospace industry perspective, or a perspective, on polymer additive manufacturing, the journey that additive manufacturing has taken over the last several decades. So the 1990s was really based on a lot of the earlier technologies, of course, like stereolithography. These technologies were applied to applications such as tooling, rapid prototyping, and manufacturing. And it's very appropriate based on the maturity of the technology at the time and capabilities. You'll see in the bottom left corner the mod repair kit for aircraft repair out in the field as a good example of that. And then above that, a drill jig that was incorporated and used in the aircraft assembly line. And that particular drill jig, I know, saved 90% of the cost and over 90% reduction in defects compared to the hand drilling method. So even back in the 90s, there was some significant impact to the industry, though at a smaller scale than you see today. In the 2000s, that's when you started to see materials used, AM materials used for end-use applications, ground stations, software test panels, and kind of lower flight requirements. A good example of that is the environmental control system duct shown above, which is made from laser strips of nylon, which was typical of the materials used in those early days especially. That's on unmanned systems, again, typical, but not always the type of system that these were deployed on. So in the 2010s, we started to see, enhanced capability for these materials. The materials became better, the equipment became better, the processes were more controlled. So, combining those, we were allowed and able to incorporate them into more stringent requirements for flight products. An example of that is the PEC material that Regina will be talking about here very soon. We've seen limited design optimization at this point, mostly on an R&D basis. I think you'll see a lot more of that in the future, but we still have to demonstrate the ability to truly design and analyze and repeatedly, convincingly for ourselves and our customers that we know how to analyze for these new design methods, such as lattice structures, generative design, topology optimization, and so on. So moving on to circa 2020, we've seen a lot of activity in the last few years that, this area just continues to grow and continues to make huge impacts to the aerospace industry. An example of that, where I've seen a lot of work, is in large area tooling. So examples of those are, the BAM process, Thermwood, and Ingersoll developing, composite cure toolings that are now in the tens of feet of length, and trying to understand how that can be utilized for making composite structure in the aerospace. Additionally, we continue to enhance our polymers. An example of that is the FTM Ultim 9085 aerospace qualified material, where not only is the performance better, the controls are much tighter and allows us to use those on air vehicles such as the Boom Supersonic Leader duct shown above. RF application, R&D, continues to be an exciting and growing area for this for additive manufacturing polymers. A lot of exciting work going on in there, and Josh Martin from Fortified 3D will talk more about that also. One of the emerging areas that I find, very exciting, extremely exciting for aerospace is polymer composites R&D. And what I mean by that is continuous fiber composites. I'm starting to develop the initial capabilities for using continuous fiber composites added in manufacturing in the aerospace. So on to 2020 plus. This is where I get to prognosticate a little bit and talk about the future applications. So again, continuous fiber additive manufacturing composites. So eventually, after you've demonstrated at lower capabilities and demo vehicles and so on, the idea is that we can start applying this capability to full production, highly structural aerospace components, multifunctional designs, another exciting area for additive. And here we're talking about how you combine functions such as antennas with structure to create like a formal S-band array shown up in the corner. Can we embed wiring for structural health monitoring? I really see a lot of impact by merging or converging these two areas. Can you imagine what we can do when we can start to integrate these multifunctional designs with highly structural polymer composites, and what kind of impact and paradigm shift that's going to have in the aerospace arena. And then the third item I wanted to talk about was the highly integrated subsystem designs. And what do I mean by that? And where's that coming from? So I don't know if you know, but especially on smaller aircraft like fighter aircraft, volume is at a premium. We actually cannot install everything and every capability we want to in a fighter aircraft. There's just not enough room. With technologies like AM polymers and leveraging those AM design freedom that we obtain that technology, we have the opportunity to completely redesign the subsystem. For example, we could take an entire environmental control system and redesign that, eliminating the clips and the brackets and the bulky ducting. A lot of those designs are based on the fact that that's how we can make them. We can actually optimize for volume, taking up minimal space while potentially even increasing performance. And this would allow us to integrate additional capabilities into our fighter and other platforms that we don't have today. So all these exciting areas are just some of the things, some of the features associated with polymer additive manufacturing. Next chart, please. I'm just going to touch on a bit on the development approach for flight products. It's actually fairly standard for additive manufacturing. It's not new. It's a process that's been honed over quite a decade. And the main thing that I'd like to emphasize here is probably about the fifth bar from the top, and that's the material process. It not only needs to be optimized, it needs to be well-defined and tightly controlled before you start to do the performance characterizations and validating the performance, including allowables generation. Otherwise, that entire effort for that performance development and allowables generation could be just complete waste of effort and time and funding. And that bar there is probably 2, sometimes 3 years to develop that really extensive database. So just a word of caution, make sure your processes are extremely well-defined, controlled, and optimized before you really go into characterizing those performance aspects for certification and qualification. But with a focused effort, you can deploy your technology in 3 to 5 years for lightly loaded applications. Potentially longer, probably longer when you start talking about multifunctional loaded applications. Now you're dealing with more than one capability that you have to truly understand and be able to model, analyze, and predict. Next slide, please. So with my last slide, I'm just going to touch on, it's actually pretty much a summary of the last slide of the waterways. But any new material or process for aerospace really should satisfy Lincoln's 5 factors. And you may be wondering who's Lincoln. So Dr. Jack Lincoln is credited with developing the modern aircraft structural integrity program, and is credited with creating that robust process. It's actually not just adopted by the DoD, has been adopted by the commercial aircraft industry and considered primary reason for really the improvement in structural integrity in aircraft in the last 4 decades. But again, emphasizing you need to have that stable material and process. That's probably key number one aspect of this. If you don't have that, the other things you can't move forward with the other. But process needs to be producible, scalable, not just something you perform in a lab, but scale to production level, sizes, rates, and requirements. Well-characterized performance, and not just well-characterized. Can you predict performance? Can you predict where and when things are going to fail? And then finally, they must be supportable. Is it repairable? Can you inspect it? And not just inspect it leaving the factory, inspect it on the aircraft. So with all of these things and all of these factors and approaches, there's a well-defined path for integrating additive manufacturing polymers on aerospace platforms. And so with that, we will move on to our next speaker, Regina Penn from Excel.
Thanks, Eric, and thanks for leading me off on the topic of the importance of repeatable, proven process control and materials control. If you go to the next slide, the problem that Eric's talking about is a problem that new materials adoption, including additive manufacturing, has. And if you're not already in working with additive, here's an analogy of what that is. If you're designing in metals, you can call out the sort of metal that you want to go work for. Aluminum 6061T4. That tells you the composition of the material that you're working with, and it tells you what's happened to that material before you get your hands on it. It tells you something about what its heat history is. It tells you what you can expect for its strength and its elongation and things like that. And that's really key data to decide what material you're going to put into your vehicle, whether that's a satellite or something that's earthbound. And one of the problems with additive manufacturing has been, how do you get that level of material repeatability and material assurance that you need to introduce these materials into your vehicle? In every way, it's different from talking about a metallic alloy. You have companies like Hexpeck who have really great materials. The material I'm going to be talking about today is our Hexpeck 100 material. That's a blend of a high-performance thermoplastic called PEK, polyether ketone. It's a cousin polymer of PEEK, if you're familiar with that. We combine it with carbon fiber for both mechanical integrity and ESD compliance. So you have the element of what is your material. And what these applications demand is rigor and robustness and quality assurance around what that material is. So in our case, for example, the way we assure that is ensuring that our raw materials are fully traceable, doing QA on what material we're bringing into the plant and turning into the raw material for the 3D printing process, and then rigorous control over where that material is, how it's stored, how it's handled, and making sure that all of that is documented and encased within an aerospace quality management system. It sounds very simple, but it's an absolutely critical part of any aerospace fabrication process. Then you have what machine are you using to actually make the hardware that's going to fly. Our team uses an EOS model printer. The model P800 is what we use. And so as a parts fabricator, which is what we are today, the question is, how do I know that the part that I'm printing today is going to give me the same mechanical performance as the part I'm going to print tomorrow? If I'm sending up an array of 10 satellites, I have to have the bracketry on all 10 of those satellites perform the same. And so it's a very important burden on folks who are supplying these flight-ready parts to prove that you have a lockdown, an understandable, an auditable, a traceable process for doing that fabrication, which includes, among other things, close tracking of the software versions that you're using on these printers, a very good understanding of what are the components that are going into them. You know, some of these printers at this point have been around for many years. The P800 has been a workhorse for us for many years. So really understanding, you know, what are the seals, what are the lasers, what are the things that are going to be needed to keep these machines operating consistently with how they've been operating in the past. Again, so I know that the part that we're providing today is the same as the part that we're going to provide tomorrow. That it's absolutely, imperative if you're going to be supplying 3D printed parts for aerospace. And then the process for removing the part. One of the things that's unique about our process that we're very proud of is the unsintered powder, so the cake material, where the laser does not turn it into a piece of hardware. We reclaim that material, and we're able to reuse it to produce subsequent production parts. It's one of the reasons our material is very cost competitive. We buy our way on to both new designs and then also retrofit applications. But how do I know that the part that I'm breaking out of the powder today is going to perform the way that I've historically proven that our parts can perform? If you can go to the next slide, we'll show you how we've handled that. We've handled that by demanding robust, continuous quality control. So every one of our production parts is printed with an array of about 30 QA specimens. And you can see there in some of our example nests, penciled in and out of plane. We're checking specific gravity. We're checking electrical conductivity, make sure that carbon is well homogenized. And based on that, we know what does a conforming Hexpeck manufactured print look like. It looks like a print where these 30 coupons perform within this certain range. And if we can prove that the parts that were printed with your bracket or your duct fell within this range, then we can tell you what the performance of that piece that you're going to put on your satellite is going to be without having to do a destructive test on that piece, or without having to do, another way folks try to solve that, a piece part qualification. You can get to a material and process-based control and qualification. And that's so important for adoption. It's just not practical for every single piece of hardware to go through a full 2-year qualification process. There has to be a way that you have the lockdown on that material and that process and that check as the manufacturing goes on. For Hexcel, if you can go to the next slide, we've generated our allowables in a couple of different ways. We worked back in 2014 with industry partners, including Northrop Grumman and the America Makes organization, who's just a great organization for helping investment in U.S.-based additive manufacturing. So back in 2014, we were generating materials allowables, proving that over repeatable builds on different machines in our fleet, on different lots of material, we had the lockdown of that material and process control. So there was a defined and well understood range of performance you would expect from Hexpeck hardware. You go to the next slide, and that approach of getting to your material assurance, your material allowables through repeated testing and thorough documentation is how we're continuing to adopt today. It's how we've made it onto vehicles today that we're supporting. We're a production supplier to multiple primes and tier 1 subs, including Boeing, where we've supported, among other things, their Starliner vehicle, and Northrop Grumman, and I'll show you in just a minute some parts we've supported those teams on. And then the next step for us is making that data and those specs available to a wider range of the public. So next year we'll be releasing an NCAMP materials database, including specifications, so that way everyone in the industry can take that data and use it for their design. We're really excited. We're going to be the first powder bed laser fusion process on the polymer side for the NCAMP team to qualify. So we're very excited about that. You go to the next slide. Wanted to end this part of the talk with some examples of, again, where today we are providing hardware because we've got that basis in the repeatable and auditable materials and process stability. So we're supplying hardware to Northrop Grumman. I love supplying parts like this, duct style parts, especially ones where the high performance, the high temperature, and the chemical compatibility of the PEC really makes some of the nylons or things like that poor material candidates. And go to the next slide. A lot of folks were supporting in the satellite area. One really important thing about PEC is it's an ultra low outgassing polymer. So whether that's a satellite application with sensitive electronics or a crewed space application, that low outgassing is a really critical material property. And then next slide, I love replacing casting style parts. Nothing makes me happier than getting a casting out of a vehicle. The near net shape design philosophy works very well, going from cast metal to 3D printing. And then finally, ducts of all shapes and sizes. As Eric said, volume and envelope. If you go to the next slide, volume and envelope end up being key on a variety of applications. And so 3D printing things like ducts is a great way we can contribute to envelope control and weight reduction. And that's what I had, folks. Thanks so much.
All right, thank you, Regina. And next up, we have Joshua Martin from Fortify 3D.
All right. Thanks for the intro, Eric. Great job, Regina. Okay, if you could move to the next slide, Susie, that'd be great. All right, just a quick intro on Fortify. We are a venture-backed startup coming out of, or based out of Boston, Massachusetts. We are an OEM and materials manufacturer, and so today I'm going to share a little bit more about our platform and how we're positioning ourselves in the market. Today we do a lot of work with a variety of product OEMs as well as contract manufacturers and have a rich ecosystem of material partners that I'm looking forward to sharing. Next slide. So opposed to the method of production that Regina just shared, Fortify is focused on a light-based thermoset system. This type of manufacturing process has been around for quite a while, but quite frankly, the chemistry hasn't really changed much in the last 20-odd years. It's known for really high resolution and typically suffers from poor mechanical properties or poor multifunctional performance. Next slide. What's interesting is if you contrast that against traditional fiber-filled systems, composites, that are polymer matrix based, there's a large difference in terms of manufacturability and cost, where a lot of these great multifunctional fiber-filled systems are very expensive or challenging to manufacture. Next slide. And so our real goal here is to combine the best of both worlds, enabling a photopolymer composite-based system that can produce multifunctional materials and high complexities at scale. Next slide. So there's going to be a video on the next slide that'll talk through a little bit more of the platform. We are a whole stack company, if you will, meaning we have unique hardware, software, and materials that we're all building together. And so next slide. This should trigger an animation on the next click. And so we are innovating at this intersection of hardware, software, and materials. Our platform is the first to have an onboard heating, mixing, and material monitoring system called continuous kinetic mixing. This allows us to process really viscous, high viscosity, and heavily filled materials. Some of these systems are close to 50% by volume of dense ceramic material, for example. And on the platform, we also use magnetics to orient short fiber reinforcement. Here you're actually looking at magnetized carbon fiber to control for mechanical, thermal, and electrical properties. Our software suite allows you to go through the standard part orientation, supporting workflows, and we even have a data dashboard or a backend that allows for better quality analysis of the materials and better part tracking for improved yield. And so this is just to give you a sense of some of the platforms that we've started shipping this year. And what I'll do next is talk a little bit more about what this platform can enable. So if you wouldn't mind going to the next slide, it should kick off a quick, thanks for, back one more, if you will. Perfect. So we are leveraging different types of additives, whether it's metallic, ceramic, or even glass fiber, for example, to drive different parts of material performance. And so I'll touch on a few application spaces that use some of these unique attributes. And if you wouldn't mind playing this video, it'll just give you a sense of our key thesis here, which is that most photopolymers on the market today are neat. That is to say, they're pure polymer chemistry. And we believe that this can only take functional applications so far. And so we're demonstrating here a neat material on the left and that very same material reinforced and aligned using our technology, and we're able to double the mechanical performance in this fairly straightforward test. Next slide. One application that we do a lot of work in today is on the tools, jigs, and fixtures space. Injection mold tooling, typically cut out of metal or low carbon steel, can be directly printed using our platform, taking advantage of the high resolution nature of light-based printing and the mechanical thermal improvements from the additives. And I think we can just skip this video here. I'll do a little voiceover if that's playing. So we have a large portfolio of materials that we have injection molded on our tools, including glass-filled nylon and even for metal injection molding based applications, stainless steel. And so I think this could play a strong role on some MRO applications where you may not want to pull a tool out of inventory if it's a particularly old component, or may want to use this to accelerate the product design cycle. Okay, so we're going to switch gears a little bit. If you go to the next slide, what gets me really excited in the additive manufacturing space is this focus on end-use part production using materials, a unique combination of materials, process technology, design technology that get you to a price or performance curve that you can't get any other way. And this is one space that I think fits that those characteristics quite well, which is in the RF electronics space. What we're bringing to market here is the lowest loss system to be 3D printable, especially on the photopolymer-based platform, where we can start to create what you're seeing here, lenses for high-frequency millimeter wave, in particular, based applications. And so if you go to the next slide, to give you a sense of what this can be used for, many of our users today are producing beam steering lenses using this type of approach, where if you look at the standard phase array technology, which can be powerful, it can be pretty expensive, has very limited field of view, and requires a ton of power. We're really bolstering the standard phase array tech using these type of passive dielectric lenses. And if you go to the next slide, just to give you a brief example of how this can be used for even antenna-based applications. This is done by one of our partners, Deluxe, showing how a dielectric lens can be printed and effectively be used for a wide beam application, in this case, across the 26 to 40 gigahertz band. Next slide. And if you compare some of these low loss materials with a standard SLA resin, this is a comparison of just a standard 2-to-1 Lundberg lens. The takeaway here is that we're able to effectively double the signal at the same power, or maintain the same amount of signal transmission at half the power, which has tremendous applications for the antenna and radar space. Okay, I just have a few more slides here to talk about some of the materials we have in development. And if you wouldn't mind going to the next slide, I'll focus a little bit on CMCs, mainly CMCs, high temperature pre-ceramic matrix materials. But for those that are interested, please check out the website. We're working to push out an ESD compliant material, as well as have a few exciting thermally conductive, electrically insulative materials that are being applied towards heat exchangers. And let's go to the next slide here. This is work that's really done in partnership with HRL, but the idea is that you can take a photosensitive pre-ceramic material that upon pyrolysis will convert to an amorphous silicon oxycarbide matrix. And the effort here is focused on how can we use Fortify's ability to reinforce and align particularly silicon carbide whiskers in this pre-ceramic resin to achieve a highly manufacturable silicon oxycarbide ceramic matrix composite. And if you go to the next slide, this material that is relatively turnkey on our platform has achieved very impressive mechanical and thermal properties, where the goal here is, can you operate above 1300 C while still basing the technology off of a polymer driven 3D printing material. And so I believe that brings me to the end of my time slot here. If you have any questions, please feel free to reach out. It's just josh@3dfortify.com. And of course, you can always head to the website to learn more. Thanks.
All right. Thank you, Josh and Regina. Great presentations and very insightful. I really enjoyed both of them. So thank you again. So I had a question for you, Josh. I couldn't help but notice that there's an announcement that came out this morning on $20 million in Series B funding led by Dakota Capital for your company. Can you tell us a little bit about that and what's that going to enable you to go do?
Yeah, that's a well-placed question there, Eric, and good timing.
I thought the timing was great, actually.
Yeah, you know, that actually it seemed a lot more, the timing worked out really well. So yeah, Coda led our Series B. Coda's a great investor for us. They have strong adjacencies in, with investment in Movandi on the millimeter wave space and Dendrite, an additive manufacturing software company. And really the goal of this round is to bring our systems to general availability, transitioning manufacturing and robustness there, while building out the go-to-market team on two of our key application areas.
Great.
Yeah, thanks for asking.
Of course. I was intrigued. I thought the timing was just, you must have planned it. Right. So I'm going to have a question from the Q&A here, and I'm pretty sure this is directed at you, Josh. You control the fibers in different directions for different layers, and you have the reinforced fibers at specific locations.
Maybe two questions
both of you, actually. Why don't you go, Josh? Yeah, there are two questions.
Great, sure. And I'd love to hear how fiber orientation plays a role in the Hexel process as well. Essentially what we're doing is, again, applying magnetics within each build. The simplest way to do it is to just have a uniform alignment per layer, but we can change the orientation and program different voxels, three-dimensional pixels, using light. And so, short answer, yes, you can control the fibers in different directions for different layers, as well as different directions within each layer. We do have presets that are meant to strike an optimization between print time and performance of your part. So for our 3D printed tools, for example, there are a lot of presets that fit the geometries that we process every day that can speed up the print process as well.
Regina, do you want to talk about being able to control fibers in the various layers also?
Sure. So the short answer is we don't. So the key part of our system and our approach is the repeatability and the homogeneity. And so one of the things that means is we're deliberately making decisions to not do, for example, within the same part, modifications on how the same part is printed. So with some other 3D print processes, thinking FDM, for example, you could change things like your flow or your speed to try to change how certain features will print. Going to what we're really driving for, which is the reliable aerospace grade, print it and it's going to be flight worthy approach. That does mean that some of the things the technology is capable of aren't a priority for us right now. Our priority is making sure that the material with the homogenized PEC and carbon, which means it's a random placement, but it's that same random placement throughout the entire body of the part and throughout repeated builds of the same part. But I think we're just on the beginning of what we're going to be able to do with these technologies. A big enabler for letting advances in, or I'll say customization of parts and tying that in with things like material and process qualification is really going to be the monitoring. So in situ monitoring, which is being able to tell during the manufacture what's happening to your feedstock, right? Whether it's a powder-based, or I'm sure Joshua has some similar things with the Fortify system. Being able to understand as the manufacturing is happening, what is the quality of the part that you're making, and being able to tie that information in with a reliable, robust database of what makes a good part. I think when we as an industry can really tie those things together, you're going to be able to have repeatable, reliable, blessed by the FAA and YASA and everyone like that, while at the same time having some of that performance customization within the same part. It's a great question, and I hope I answered and gave you a little more there.
So is Hexel working on new materials with PEC? And what I mean by that, different fillers, higher levels of fillers to get different performance characteristics than you do today?
Yes, absolutely. So we currently have 3 materials that are market ready. What I talked about today is our Hexpeck 100, which is the PEC with the carbon fiber. We also have a pure PEC resin material, a neat option. As Josh kind of hinted to, the neat resins do have some lower mechanical performances, but they're electrically insulative, which is important for some applications, and also invisible to radar. So we see a demand on it for part families like radomes. We also have a material that we launched last year. It's our Hexpeck EM, and a nod to some of the stuff Josh was talking about. So this is a material that has higher levels of conductivity and some really interesting RF characteristics. So we've gotten a lot of pull from that for folks doing things like shielding, EMI shielding, or shielding from other sorts of electricity.
Great. Sounds like you have a lot in the hopper there. So a question for you, Josh, from someone in the audience. For these photopolymer resins, are they UV stable? Are they UV stable post-cure, or do they need to be coated?
Yeah, it's a great question. Hopefully my mic's live here. I've got a double mute system that sometimes I get stuck on. And short answer is it's always more reliable to have a coating for long-term stability. Since we're filling these resins with very opaque additives, you're not seeing the same amount of degradation, especially within a complex part. If it's going to be a lattice, for example, it's not getting the same type of dose in the middle versus the outer exterior. But the short answer is we're still working to better understand how filling these systems increases UV stability. A lot of that is going to be based on what type of hybrid chemistries we can leverage as well. And so we do partner with groups like Henkel that have more UV stable chemistries that they've been able to release on other platforms.
Right. So another question, I think I'm going to add on a little bit, but Materially's blueprint is promising 100% reusable PA powder. Can you elaborate if Hexel has a similar solution? And I guess what I'd like to hear is, how many times can you reuse the powder? Do you have data that supports the powder reuse and how long you can use it, or how many times you can reuse it?
Yeah, that's a great question. So we currently have where most of our customers are accepting our second-use powder, so up to 2 reuses of the powder, and we're working on the database to make that 3 material reuses. Going back to that material and process validation, because of our tight performance control, we can't just introduce a new recycle level. We have to take the time and prove to all of our customers that the material that's an additional recycle level is as good as any of the other levels. The recycled powder actually ends up with higher mechanicals than the first-use powder. So, we have to have conversations with customers about, the commercial benefit with having all the recycle levels qualified, and assure them, that there's not a degradation in performance. I think folks have a first reaction to reused powder, believing that it's going to be an inferior product. It's not. We hold our reused powder to exactly the same QC standards, exactly the same tests that we hold our first-use powder to. And we maintain traceability of what's in that powder going all the way back to the first time we put that powder together here on site. So maintaining that traceability is really, really important. There's a lot of challenges that come with using a higher performance thermoplastic like PEC multiple times. The way it responds to those cycles is different than how some of the materials that need lower heat, like a lot of the nylons, end up having. So we consider it a really important advantage that we're able to offer those recycled powders, and I want to keep pushing the envelope on it.
Right, great. So I have another question, and it's going to be for both of you. Let's start with you, Josh. How tight can you hold tolerances on the parts you make?
Good question. So we guarantee at least plus or minus 5 thou across the build plate, which is roughly 6 by 8 by 13 inches for our current system. However, and that's if you're going to print a part for the first time. However, you can get to plus or minus 2 thou, especially if you're willing to optimize the print parameters so that you can produce multiple of one part over and over. But plus or minus 5 thou is the place to start.
And for you, Regina, can you answer the same question?
I can. It's going to be a slightly higher number. So, we do have some wider, tolerances for that first run, right? As Joshua said, once we've seen a part the first time, there's a lot of optimization we can end up doing. We look at the longest diagonal length of a part. So we've got buckets that fall within shorter than 8 inches all the way up to larger than 16 inches. And so based on that, we assign an expected profile tolerance. For those of you familiar with that. The profile tolerance ranges go from plus or minus 60 to plus or minus 180. And that's out of line with what a lot of folks expect from aerospace design. So I get it. One of the reasons my team spends a whole bunch of time working with the applications engineer on the customer side, because again, that's our first hit, the very first time we've printed it. And what we find is for a lot of these applications, the very tight tolerances, the plus or minus 5 or the plus or minus 2, aren't actually needed for the whole body of the part. It's key interface points. It's key places where there's going to be an assembly or where there's a very, very tight envelope. So we look to understand what are those needs for the customer, and then through orientation optimization or post-processing, this material machines and bonds very, very well. We get the customers what they need for the end item. It does require more of a casting-like approach to the design philosophy versus something like a machined aluminum based design philosophy where every single thing needs a dimension, and the dimension can be very, very tight because there's going to be a drill bit hitting the whole thing.
All right, thank you. Yeah, and I think a good point there was that the aerospace industry, I think sometimes we're pretty guilty of over-tolerancing parts, and we've learned that working with you and other companies over the last few years is, do we really need that tolerance? A lot of times the answer is no. We do need it to keep it places, like you said. So thank you. Another question for you, Regina. So can you tell us why PEC is preferred over PEEK and why you're not using PEEK?
I'll speak more broadly, not just PEC versus PEEK, but PEC versus some of the other polymer applications out there. The whole package of what we can get with PEC, the high usable temperature, the chemical compatibility, the great adhesion, which, that specifically is an item that some of the PEEKs can struggle with. We have customers that need parts painted, that need parts bonded. So the printed PEC does very, very well with all of those. The outgassing is a really key element of it. Some of the early adopters with this technology, as I'm sure everyone on this panel knows, tend to be the space and defense folks. So those applications do demand materials that can be around sensitive electronics or in low pressure environments or things like that. So it's really the whole package of what we see working with that higher performance thermoplastic that is the value to the customers.
Right. So I think I have a couple questions that are a little bit more, maybe a little less technical, but a little more digging into some of the background. But what was the, Josh, I'll start with you. What was the biggest you had to overcome in developing your technology?
Good question. I would say one of the biggest challenges is the fact that we were building this unique process to then develop unique materials. And so it's this lock and key mechanism, which in the early days very much formed a chicken and egg type of situation where we needed to build a fairly complex system architecture to then go and push the limits of what we could develop on the materials side. And so it certainly helped that the research that spun into into Fortify had a strong academic foundation to de-risk some of the scientific risk. But I would say that was one of the fun challenges.
What did you find the most difficult? Was it the hardware, the software, the materials, or the whole concept, the light, UV light concept, and utilizing that?
Yeah, I think it's really the photokinetics and the rheology. In other words, can you cure the material that you're suddenly filling with very opaque additives? And can you flow it? Some of these materials start to resemble more of like a wet cement than traditional 3D printing resin. And so that required us to kind of go back to the drawing board a few times. Those are the
very, very different from typical SLA resins. Very different.
Right.
And you, Regina, what was the biggest hurdle that you and your team had to overcome with the PEC process?
You know, one of the most interesting things has actually been going back to your very first slide, right? The long history of 3D printing. I would often find we'd be in these conversations with chiefs engineers or fellows or designers, and there'd be a resistance to what we were talking about, and then it would come out. In the 90s, someone sold them on SLA, and it wasn't what they expected. So I found that, in a way, not to exaggerate a little bit, I almost had to become a therapist for, all right, what is the history of 3D printing with this organization? Is this an organization that invested in a bunch of SLA material, but then tried to put it in a fuel soak application and it fell apart and someone got very embarrassed with it, right? Is this an organization that's attempted to work, I've had this a couple of times, attempted to work with a high-performance thermoplastic and been unsuccessful internally, and now they've got other folks who are remembering that this technology has all of these risks? Is it an organization that's invested heavily in metallics? And so even though this application might be better for a polymer system, you've got some internal folks that, instead of being advocates or being open-minded, have other motivations going on. So it's really making sure that, that I could talk for an hour about the material, but really, the 5 minutes spent addressing what that specific team is worried about when it comes to production adoption, that key ends up being what it is. Because then you can speak, your concern is repeatable allowables. Well, great, here's our data. Your concern is chemical compatibility. I had a customer that was switching to our material from a lower performance polymer system because of a chemical compatibility mismatch. And so the first thing we had to talk about was, all right, well, what was the chemical that it was exposed to? Let's get some data showing that your biggest risk is something we can take care of right away. So that it really goes to the heart of material selection. What does the organization need? What does the application need? And then how do you talk through how this material and process can satisfy that?
Right. So I think what you're saying is sometimes overcoming culture and history is harder than the technology.
Yes, absolutely.
I've seen it many times. I've seen that argument many times. It didn't work 30 years ago. Why would it work now?
Exactly. And having that in a way that respects the experience that those folks are bringing. The folks that come with the most institutional concern end up being the ones who end up being the technical advocates and can help navigate. I like to say, where are the program managers with problems? Those are the people I want to talk to. So those folks end up being key with connecting us with them.
Great. I only have a few minutes left. There's one question I did want to ask. Since we've been focusing primarily on aerospace defense applications, I'd like to ask you, starting with you, Josh, what are the major applications that you see outside of aerospace and defense for your technology?
That's a great question. So at the stage that Fortify is at, we're actually not focusing on aerospace applications first, because there's sort of an inherent impedance mismatch based on the design and timelines and validation timelines. And so we've done a lot of work in the traditional jigs, tools, and fixtures space. It happens to be almost half the current additive manufacturing market size. So there's still a lot of good work and good value to apply there. Outside of aerospace, we've seen a lot of interest in an adjacent market being automotive, where you're still looking for maybe a under the hood type of polymer composite that can have high creep resistance, can find good fit with, maybe it's an electrical connector that would otherwise have to go through traditional tooling process. And more lately, we're really energized by some of the electronics space because of the opportunity fit with parts that fit in the palm of your hand, are produced in the tens to hundreds of thousands per year, and need some type of specialty polymer formulation.
Right. And same for you, Regina. Where are you seeing applications for Excel outside of aerospace?
I'll echo some of the observations Josh made. The synergy, especially in the U.S., between automotive and aerospace is well established, and we jump back and forth. Specifically, I think there's a home for this material in terms of energy storage. When you look at, especially at scale, some of the needs, when you look at how energy gets stored, whether it's fuel cells, whether it's things like hydrogen applications, or anytime you've got a chemical storage solution for these items, I think there's going to be a need for a material like a pack-based system that's robust and can get into the unique geometries that those are going to need. I certainly hope that green energy storage is something that pulls a lot of our technologies into it as it continues to grow.
Okay, great. So we're almost out of time here. You want to chime in at this point?
Yeah, hi. Yes, thank you. Thank you, Eric. Thank you, Regina, and thank you, Joshua. I really appreciate it. What a great discussion, super informative, a lot of great information shared. So thank you all for spending time with us. Special thanks to Erica, Joshua, and Regina for providing your technical insights on high-performance polymer additive manufacturing and for supporting the additive manufacturing community and SME events. Really appreciate the time that you spend with us. Very special thanks to all of our attendees who participated. We will be sending out a quick survey after this event, and we would appreciate a few minutes of your time to provide us feedback. We're always looking for ways to process improve. And again, very special thanks to all of our attendees. The webinar has been recorded or will be recorded. We will make it available on our AeroDef webpage shortly, so please allow us a couple hours. By tomorrow morning, it should be up certainly. And a quick promo for next month. Be sure to join us on April 22nd at 3 o'clock Eastern Time when we present the next satellite session, Unlocking the Digital Factory, Accelerating the Use Cases of IoT for AeroDef Manufacturers. Registration is open right now, and you're welcome to go on our AeroDef webpage and register if you choose. Again, thanks again, everybody. I really appreciate your time. Appreciate the effort. And everyone, have a great rest of your day, and we'll see you later. Bye-bye.
Bye. Thank you.
Thanks, everyone.